Section 6.4 is the last section of new material that we have to do this summer, and each of the problems in Section 6.4 is a word problem, unfortunately. And somewhere within each word problem, there is a function that's given and some words to explain what the function can be used for. The functions are maybe not perfectly real-world realistic because I tried to make the numbers kind of friendly. And for each problem, we're going to do a mixture of graphing, interpreting a graph, and solving some equations by algebra and interpreting the algebra. Their problems are too big to fit two problems on one screen, almost too big to fit one problem on one screen. If you looked at my problem 2 and compared it to your problem 2, they should look remarkably similar. All I did is change the function name. In problem 1, you have that as a function. In problem 2, I have this as a function. I don't want to steal your odd problems because there's so few problems in this section. I'm going to do problem 2. If you just wrote down the equation for problem 1, you might be able to do problem 1 while I'm doing problem 2. Would probably be a good use of your time. But I'm going to jump into problem 2 and just try it. I'm going to read the problem, understand the problem. It's a super common problem. It's the kind of problem that you're bound to see in a college algebra class. And if you take a calculus class, it's a kind of problem you're bound to see in a calculus class. So it's an important problem to end off the semester. So this problem 2 talks about an object being thrown up in the air, and I give an equation. The equation I read h evaluated at t is negative 16t squared plus 64t, where the left symbol, the function symbol, gives the height in feet that the ball is above the ground after t seconds after it's thrown. Just got done making a table and sketching graph in the last section, and we're going to do it again here. This is section 6.4. So I'm going to graph the function h of t equals negative 16t squared plus 64t. I don't have x's here, but that's not going to make me stumble. What I do have is both a squared and a first power term to the right of the equal sign. That means for the number of the middle of my x column, I have to use the negative b over 2a formula. I can't get the number by inspection, and I'm changing the word x to t because in the parentheses the variable is t, and it's going to be important to understand that the t represents time in seconds. So now my x-axis is turning into the t-axis. When we're dealing with word problems, the labels that we use gets to be important. But for what it's worth, in this equation, I don't have a c, but I don't need a c. The a is negative 16. The b is positive 64. And to get my table started, this is the kind of problem where I use the negative b over 2a formula because I have both a squared and a first power term. So I'm going to do negative 64 over 2 times negative 16. And I'm all about calculators this late in the semester. So let's do this. Negative 64 over 2 times negative 16. I get 2. That 2 actually stands for 2 seconds because it's a t, it's a time column. I'm going to make my table, and I'm going to be super specific. I'm not going to write x, I'm not even going to write t. I'm going to write the numbers in the right-hand side, which are in the x position, represents time. I'm going to put 2 in the middle of the time column, which represents 2 seconds. I'm going to go bigger, which represents 3 seconds and 4 seconds. Smaller, which represents 1 second and 0 seconds. I'm going to fill in my y columns. I'm not even going to use the name y. I'm not going to use the function symbol h of t. I'm going to write what this is. The y's are the height in feet. So this x column is the time in seconds column, so 0 seconds, 1 second, all the way to 4 seconds. And the y column is the height in feet. I need that kind of depth of understanding of the points to help myself and when I get to answer the questions. Now for each x, I'm going to get a y. So the first one I'm going to do h of 0 is negative 16 times 0 squared plus 64 times 0. I shouldn't write all that down, but I just wanted to. So for my first value, negative 16 times 0 squared plus 64 times 0. That says at 0 seconds, the object is 0 feet high. Now I'm going to change the zeros to 1, mindlessly pressing buttons. And then that next point that I generated says at 1 second, the ball is 48 feet high. When I change the 1s to 2 to get my third point, it says at 2 seconds, the ball is 64 feet high. Change the 2 to 3. I always make my vertex in the middle of the x column, so that 264 probably was the maximum point because this is an upside down parabola because the negative in front of the squared. Yeah, you can see the symmetry now. In 3 seconds, the object is 48 feet high. A lot of times I'll use the word ball here because we usually throw balls into the air, but this is object. And at 4 seconds, it's 0 feet again. So let me sketch this graph on my axes. So 0, 0 is the origin. That represents 0 seconds, 0 feet. The x-axis is time in seconds. The y-axis is the height of the object in feet. And then 1 and then estimate 48. 2 and then estimate 68. Your problem 1, if you opened up what I haven't posted yet, but I think I'm going to call them lecture notes, you can get the tables that you need if you own a printer or use a tablet. I bought my first printer in a lot of years this summer because I needed to print some of this stuff out. I had the school print out most of it, but every time I made a mistake and had to start my video over, I got to use a printer. So you can see the ball or the object goes up for 2 seconds. It reaches its maximum height, and you can just watch it go back down. The function itself, will graph and go beneath the x-axis, but realistically, this here represents underground. That's not, even though the function graphs that way, in all practical reasons, that's the only portion of the graph that I should be looking at because you're not going to get beneath the x-axis for the height. So done with part A. I made a table and sketched a graph. I've already done part B, but I'm going to emphasize. Part B says, what do the numbers on the x/horizontal axis, it's really the t-axis, and the numbers on the x-axis represent time in seconds. Part C, what are the numbers on the y or vertical axis? I've already spilled the beans there. That represents the height of the object in feet. In fact, every point at 0 seconds, the object is 0 feet high. At 1 second, the object is 48 feet high. Every point gives you a time and a corresponding height. Part D, identify the vertex. The vertex is the point 264. Part E, what do the coordinates of the vertex represents? The t is 2 seconds, and it says at 2 seconds, the object is 64 feet in the air, because the 2 is the time, the 64 is the height. Because this vertex is a maximum point, the maximum y value is 64, which occurs when x equal to 2. I could have said this. I could say the maximum, in this case, height, which is the y value, in this case the y values are height, is height equal to 64, which occurs when the time, which is the x, is 2. That's how we would have worded it in the last section, because the problems weren't word problems. But now I can use this to answer the important questions here. When does the ball reach its maximum height? Well, its maximum height is 64 feet, and it occurs at 2 seconds. So for part F, when does the ball reach its maximum height? At 2 seconds. For part G, what is the maximum height? It's the y-coordinate of the vertex. It's 64 feet. I'm short on room, so I'm just writing the numbers down, and they're proper answers to the question. Part H, find the x-intercepts using algebra. The x-intercepts, they're on my graph already. I'm going to do them using algebra just because this is an important skill to take with you. It's not technically required for us to find x-intercepts of parabolas, but you're going to need to do it in college algebra, so might as well get you used to it. Find the x-intercepts using algebra. For part H, to find the x-intercepts using algebra, I take the right side of the function and I set it equal to 0. I'm going to solve by factoring. I'm going to pull out the common factor of negative 16 and t. I'm factoring out a negative because the first term is negative. 16 is the largest number that goes evenly into 64 and 16, and they both have a t. When I factor out a negative, I change the sign, so the first sign is going to become positive. I factored out a 16, so I'm going to divide that 16 by 16. My first coefficient is going to be 1. The t squared is going to turn to t. After the plus sign, well, I'm going to change the plus sign to a minus sign, and then I'm going to divide the 64 by 16 and figure I get a 4 after that minus sign, and I factored out the t. So that's factored for finding my x-intercepts. Once I have the problem factored and set equal to 0, I set each of the factors equal to 0, and I do the algebra to solve. The negative 16t, when I set it equal to 0, I divide both sides by negative 16, and I get t equal to 0. And when I set the t minus 4 equal to 0, I get t equal to 4. That's the x-coordinates of the x-intercepts. The y-coordinates have a 0. Always, when I'm finding an intercept, the opposite letter, its coordinate is 0. So my answer to part H, the x-intercepts are 0, 0. And then it says give a physical interpretation of the x-intercepts. It's when the ball hits the ground, or when the object hits the ground, because its height is 0. So for part I can say the object, the x-intercepts tell me when the object hits the ground. It may bounce, but this function doesn't show a bounce because it goes up. It starts at 0 feet high, it goes up to 64 feet, and it hits the ground again. So that's all it is. It just tells me the object, when the object hits the ground, or I can say the object starts at 0 feet and it it lands after 4 seconds. And it may bounce, but it's not going to go underground like the graph shows. And then I'm asked to find a practical domain. Well, even though the domain of this parabola would be negative to positive infinity, the portion of the graph that shows the flight of the ball goes from 0 seconds to 4 seconds. So the practical domain, I'd probably put square brackets on it because those times are actually times that are included. The practical domain would go from 0 seconds to 4 seconds. And the practical range is the heights of the balls, the y's. The lowest the ball goes, or object goes, is 0 feet. The highest the object goes is 64 feet. Even though the range of this function is really negative infinity to 64, because this is a realistic problem, I'm probably not going to include the negative infinity. I'm going to include the lowest height, which is 0 feet, and the maximum height, which is 64 feet. The practical range is 0 to 64. I don't know if that's good or bad. I haven't done this kind of problem with this much detail in it in intermediate algebra, nor in college algebra. We don't talk so much about practical domain and practical range, but we should. So that's everything for problem 2. Your problem 1 is the twin of this problem. So you should give problem 1 a go. And your problem 3 is a twin of this problem. I'm not going to do another one of these. I'm going to let you do 1 and 3. We have one more kind of problem, and that's what I'm going to end up the video with. And I don't know if I could do it in a one-parter, so I'm going to pause and do a part 2. So you should try to do problems 1 and 3 with my shell that I've created for problem 2. They'll solve the same way. Problem 1 asks the same questions as my problem, except it had that different function with the 80s in it. And problem 3 asks the same questions as my problem 2, but it has a different function. The answers are essentially going to be parallel to the answers I created, just the heights are going to be different, the times are going to be different, but the axes are going to be the same because this still talks about an object being launched, and it's not really from a platform, it's actually being launched from ground level. So I'll take that, an object is launched, the equation gives this height, and answer the questions, exactly the same questions, kind of exactly the same theory to get the answers to them. And then we'll push through and figure out the next kind of word problem. There's 2 kinds of word problems. We've just did one of the 2. On the next part, we'll do the second part, the second kind of word problem.